10.5 is all about the binomial theorem. And they use the first little thing we're going to look at to kind of build up to the second thing. But with the second thing, there's two different ways you can do the binomial theorem. And the way that I do it, I don't use the actual binomial theorem that you can actually use. You can use Pascal's triangle, which to me is a whole lot easier because the math is a whole lot simpler. Because basically somebody does the math for you. And you still have to do some math, but you just have to clean it up a little bit. Okay, so very first thing that they're going to do, have you look at, is it's a binomial coefficient. Before you get to the binomial theorem, there's a little bit of work that comes with what you have to do with it here. And basically is this. If you have, and this kind of goes back to probability, combinations, and permutations, and statistical probability, that kind of stuff. But the binomial coefficient basically says that if you're picking, if you've got 100 numbers and you've got to pick 2, what's the probability of you picking out, 2 numbers out of this group? And you go back through and you figure out how many different combinations of things you can come up with. And this is pretty much what you're kind of going through on this one. And here's the formula that you get when you go through this part. N factorial, and that's divided by r factorial, and then n minus r factorial. Okay, and the exclamation points, those are not people that are really excited about math. If you haven't seen those in a while, that's factorials. And basically with the factorial, that just means that, just to kind of give you an example here, 5 factorial is basically saying, all right, if you have 5 things, how many different arrangements can you put those 5 things in if you're rearranging stuff? And basically is this, that with a factorial, you start with that number and you multiply by that number and every other number below it down to 1. Do all that, and that gives you the outcomes you could get from this thing. So 5 times 4 is 20, times 3 is 60, times 2 is 120. So if you had, and they usually do examples like, okay, if you had 5 airplanes that were getting ready to take off, how many different ways could those airplanes take off? Well, there's 120 different ways you can do that. Okay, now they use that to kind of say, all right, if you're going to find the binomial theorem, you're going to use this binomial coefficient to help you find some of the coefficients that are in the binomial theorem when you're doing this. And the whole binomial theorem basically has you expand some expression, x plus 2 to the 6th power. And the binomial theorem is basically a shortcut that you can do this with the numbers that you have and go through and do everything with this part. Because they don't want you to do the full method over and over and over and over and over. You can do that, but it just takes a long time. The binomial coefficient, or binomial theorem, helps you do that faster, but here's another way that's even faster than doing the binomial coefficient and going through the binomial theorem. And they give you this, if anybody has a textbook, it's on page 1091. And basically here's what it is, that way back when Pascal and all of his buddies started looking at, and this is called Pascal's triangle. And this was the age of enlightenment when everybody just wanted to think. And they just started playing around. They said, okay, let's take some expression. Take the smallest, easy expression we can come up with, x plus 1. And, what happens if we start going through and doing the full method on this thing? Now, here's kind of a good review question. If you do anything to the 0 power, if you have, if you're going to grow this thing exponentially, if you do anything to the 0 power, how much is there? If you're going to grow something exponentially, you've got to have something there, right? So there's still that 1. That anything to the 0 power would be 1. And now, y'all can kind of wait. You don't have to necessarily write this down. Y'all just kind of watch and see how this goes. And they said, okay, what happens if we did x plus 1 to the 1st power? Just be itself, right? So it'd be x plus 1. And they started kind of playing around with this and started coming up with some things. And they said, well, number-wise, we just do coefficients. We get 1x and a 1. All right, if we did x plus 1 squared, we went back and did the full method, work this thing out, you would get x squared plus 2x plus 1. So they said, all right, well, that's 1, 2, 1. And then they just kept running this thing out, going, x plus 1 to the third. And finally, one of the guys in the group noticed something, that when you get to this point, it came out you're going to have 1x to the third, 3x squared, 3x, and then a 1. And somebody started looking at it, started playing around with it, and they were like, hey, wait a minute, there's a little bit of a pattern once we started going here. That if I want to do x plus 1 to the fourth, instead of doing the full method over and over and over and over, they noticed that, anytime you do 1 to a power, doesn't matter what it is, it's going to be 1. So this last number is always 1. If you do 1x to the power, it's just going to be x to that power, so this one's also going to be 1. And then somebody kind of noticed, they said, well, if you kind of look at how this thing is set up, if you take the numbers directly above it and add them together, you get the next number that's below it. So for this one, you could take 1 plus 2 and get 3. 2 plus 1 would also be 3. And so they started checking it, and they were like, okay, does that work if we keep going through this thing? If you went back and did the full method, sure enough, if you did 1 plus 3, this next number would be 4. You could do 3 plus 3 and get 6. You could do 3 plus 1 and get 4. And it keeps going and it keeps working. And now it's still based on the same thing, that if you do x plus 1 to the fifth, you still put a 1 here, you still put a 1 here. But instead of doing the full method over and over and over, just take the numbers above it, add them together, that makes 5. 4 plus 6 is 10. 6 plus 4 is also 10. 4 plus 1 is 5. So instead of having to do the full method over and over, they started figuring out, okay, we've got a little shortcut here. So if we want to go to the next number, do x plus 1 to the sixth. Same thing, we put a 1 here, put a 1 here. 1 plus 5 is 6. 5 plus 10 is 15. 10 plus 10 is 20. 10 plus 5 is 15. 5 plus 1 is 6. Now, and if you had to go back and multiply these out, you would start with x being to the fourth power. That would be your highest number. And then the next one down would be 1 power less. So this would be 4x to the third. Then you would have 6x squared. Then 4x. And again, there's always 1 times 1 times 1 times 1. So it's just a regular number of 1, and then we're good to go. And you could take that triangle, and that's Pascal's triangle. You can stretch this thing out as far as you want to go. But once you get the first couple of lines in there, you can just keep adding and going down through that one. And you start noticing some little patterns that, the after the 1 and right before the 1, these two numbers are always the same. This is 5, this is 6. If you go to the next one, they would be 7s. If you go to the next ones, they would be 8s. And it kind of keeps working down. And there's always this balance to it that, the first number, the second number here is always going to be the second number that's here. The next two numbers, these two are the same, just like these two are the same, just like these two are the same. So there's always these little patterns that pop up on this thing. Well, one of the wise guys in the group said, okay, well, that's great if we're going to do x plus 1. But then somebody said, all right, what if we want to do x plus 2? And I was like, oh. So that changes things, because now instead of doing 2 times, when the full method, instead of doing 1 times in the full method, now you got to do x plus 2 to the 6th power. So here's basically what you can do. Now they're going to tell you to use the binomial theorem if you want to. If you know the binomial theorem and you want to use it, knock yourself out and go for it. But we're going to use Pascal's triangle. And we're going to use this to expand the expression. We'll do 2 or 3 of these just so you can kind of get the idea of what you're doing. Okay, now, here's the steps you're going to do for this part. There's basically 3 parts here. First thing you're going to have to do is you've got to determine which row of numbers you need from Pascal's triangle. And to do that one, what you've got to do is whatever the power is they're asking you to expand, the power will always be the second number that's in that row. Because the first number is always 1, so you need the power to match the second number. So the power of the expression has to equal the second number in Pascal's triangle. And we'll come back and show this out, but just kind of flashing back real quick. So for the problem we're wanting to do, we're going to do, what was the problem? We're going to do x plus 2 to the 6. Okay. Now we'll come back and do that. We'll actually put all the work down in a minute. So if we were kind of writing this part of it out, we've got x plus 2 to the 6th. Since we've got the 6th power, we need the second number to be 6. So for ours, we're going to use this. There's the 6, so that tells us we've got to use this row. If it was x plus 2 to the 5th, 5 would be the second number, so we'd have to use that row of numbers. Okay, second thing. We've got this expression x plus 2 that we're going to do. Again, that can change. It can be t's or y's or whatever it's going to be. But we're going to write the first term in descending powers. And we're going to put that under the numbers in Pascal's triangle. So for us, we've got x, and basically you're going to start with x to the 6th power. Next term will be x to the 5th, x to the 4th, x to the 3rd, and just keep counting down and going from there. And then really the last thing to set it up before we do all the parts we've got to do, step 3 is you're going to write the second term in ascending order, or ascending power order, I guess would be the best way of saying it. And start with a 0 power. And again, anytime you do anything with a 0 power, it's just going to make it a 1. So, you kind of default on that one. The first number is going to be 1, just like we were going to do in the triangle. Okay, and that one will also be under the numbers in Pascal's triangle. Get tired of writing this, so we'll start constant shorthand here. So put under the numbers in Pascal's triangle. Okay, so far with those, you're not, haven't really done any math. You pull out the numbers, the row of numbers you would need from the Pascal's triangle. You're going to write one term in descending order. You're going to write the next term in ascending order. And then the part where you actually do the math here, step 4, is you're going to multiply each column of numbers to get the terms of the expanded expression. Okay, so first one we'll do, we're going to do x plus 2 to the 6th. Okay, so very first thing, and again, don't cram this in, leave it out kind of wide because it's going to give us some room to work here. The row of numbers that had 6 where again power was 6, so the second number is going to be 6. Those numbers were 1, 6, 15, 20, 15, 6, and 1. Alright, then we're going to take the first term, which was x, start with x to the 6th power, and then count it down. So x to the 6th will be here, x to the 5th is here, x to the 4th, x to the 3rd, x to the 2nd, x to the 1st. And at the end, you still go to x to the 0 power, which, again, it'll still be 1, but that's okay, because we'll take care of that in a second. And then we're going to take the 2, which is the second term, and it's going to go opposite. It's going to go up a power. To the 0, to the 1st, to the 2nd, to the 3rd, to the 4th, to the 5th, and to the 6th. And from there, we're going to work everything out in each column. And as you work those out, that's going to be your individual terms. That's going to be the answer that you would get is if you had taken x plus 2 and had done the full method over and over and over and over, you know, that would have been the answer that you were looking for. Okay, now here's what I like to do when I'm going through these. You've got your numbers up here from Pascal's triangle. Those are good. As long as this is just a variable, where it's just x or y or t, whatever, this part of it's good. The only thing you really may want to do is here at the end where you've got x to the 0, you may just want to scratch that out and put a 1, because anything to the 0 power is going to be 1. And you could basically do the same thing here. Just scratch that out and put that as a 1. Okay, with the other numbers here, because you're going to have one set of numbers you're going to have to multiply out. You've got 2 to the 1st, 2 to all this other stuff. I would go ahead and kind of scratch these out at the same time as well, and just put what that number is. 2 to the 1st is 2. If I do 2 times 2, that makes this a 4. If I do 4 times 2, makes this an 8. And that way it's a little bit easier because now you just take the next number and keep multiplying by 2. 8 times 2 is 16. 16 times 2 is 32. 32 times 2 is 64. Okay, and now here comes the math part. Multiply everything together. 1 times 1 is 1 times x to the 6 makes that one x to the 6. The next term is you've got 6 times 2, which is 12, x to the 5th. 15 times 4 is 60, x to the 4th. 20 times 8 is 160, x to the 3rd. 16 times 15 is 240, x squared. 32 times 6 is 192, x to the 1st, or just x, and at the end 1 times 1 times 64 would make it 64. And that would be x plus 2 expanded out to the 6th power. There's a lot. There's other ways. It's definitely a lot longer than doing that. And okay, let's do one more of those, and then we'll kind of backtrack because I forgot to show you all the binomial coefficient parts of it. Actually, we'll do 2 more of these. Let's do x minus 3 to the 5th. Now, and if there's a minus, like this one is, we'll show you a trick. Don't worry about the minus, the sign that's there when we're going through and doing the numbers. Don't worry about it because it'll work its way out the end. We're going to show you one more thing to do here. So for this one, again, we've got x minus 3 to the 5th, so we know that 5 has to be the second number. So that means we've got to use the numbers. It's 1, 5, 10, 10, 5, 1. Okay, I'm going to scoot that over because that was a little bit too close. 1, 5, 10, 10, 5, 1. Okay, so no, you will not have to memorize Pascal's triangle. Okay, second thing we're going to do is we're going to take x, start with it to the 5th power, and then count it down. x to the 0. And if you get there and you want to go ahead and scratch that out and just put a 1, feel free to go ahead and put a 1 there. Okay, and when you count up, don't worry about the negative. Just forget the negative. Just do 3 to the 0 power, 3 to the first, 3 to the second, 3 to the third, 3 to the fourth, and 3 to the fifth. We'll come back and get the negative at the end because it's a lot easier to do the negative at the end and just kind of clean it up without having to worry about the negative in the middle. And because some people get worried about, well, what do we do with the negative? Okay, don't worry. We'll get it straightened out here in just a minute. It's a lot easier than worrying about it here. Okay, and again, for me on the bottom, I like to take these numbers and go ahead and, instead of leaving it like this, now go ahead and write it out. Just take that few extra seconds to write those out. But then actually go back and multiply these out. Again, anything to the 0 power is 1. And actually scratch them out so you don't, because I've had people that would leave them in there and multiply it up a couple times. So scratch those out. That's going to be a 3. 3 times 3 is 9. 9 times 3 is 27. 27 times 3 is 81. And 81 times 3 is 243. Okay, and then just one column at a time. You got 1 times 1 times x to the 5th. So that's x to the 5th. 3 times 5 is 15. X to the 4th. 9 times 10 is 90. X to the 3rd. 27 times 10 is 270, x squared. 81 times 5 is 405, x, and then 243 times 1 is 243. Okay, now, and here's the one thing you will do. If this is a minus up here, with this problem that we're doing, when you have the minus, all you have to do is just alternate your plus or minus signs. And the only thing that happens with this one is that the plus sign has to go first. Because it's a positive x. Anytime you do x times x times x, it's always going to be positive. So this would be a positive, which we don't really need that positive. This would be a negative, positive, negative, positive, and then a negative. Because if they don't make this one too short, the numbers get big in a hurry. So let's do 5x minus 1 to the 3rd power. Okay, again, 3rd power, so the second number has to be a 3. And if we go through our list of numbers, that was 1, 3, 3, 1. Okay, now here's the one little twist on this one that makes this one a little bit more complicated than the other ones. Because the first term that's here is not just x, it's 5x. So for this one, you have to do 5x to the 3rd power. And then 5x to the 2nd power. 5x to the 1st power. And then 5x to the 0 power. And the one break they give you for this one is that, okay, we had to do 5x to these powers for this particular problem. They're going to give you probably a little bit of a break so that you're going to do 1 to the 0 power, 1 to the 1st, 1 to the 2nd, 1 to the 3rd, which means it's 1, so it doesn't really matter because all those will be 1s. Okay, so 1 to 0, 1 to the 1st, 1, all that's just doesn't matter. Scratch the work you actually is x powers, numbers. Because it's not just x to the 3rd, it's 5 times 5 times 5. So if we scratch this one out and drop it down here, it would be 125 x to the 3rd. If we scratch this one out, it's 25 x squared because it's just 5 times 5. So on all these, 5x to the 1st would be 5x, and anything to the 0 power for this one is still a 1 that's on that part. Okay, so you've got 1 times 1 times 125, which is 125x to the third. This is 25 times 3, so that's 75x squared. This is 5 times 1 times 3, so that's 15x. And that's just a bunch of 1s on the end, so that's a 1 there. And this one was, it was a minus, wasn't it? Yes. So we're going to alternate. First one is positive. Second one is negative, then positive, and then negative. So the only part that really makes this one the least little bit complicated is when they put a coefficient with the x, because then you've actually got to go through and multiply those out. But again, those numbers shouldn't get too big, because if not, the numbers start getting really, they get into the thousands and 10,000s pretty quick if you do it that way. Okay, and here's the last thing, which should have been the first thing. I didn't give you any examples of doing the binomial coefficient, so let me do that for you real quick here. Okay, let's do 8 over 3. Alright, so that's 8 factorial over 3 factorial, and then you're going to do 8 minus 3 to make it 5 factorial. Okay, and again with the 8 factorial, that's 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. 3 factorial is 3, 2, 1. 5 factorial is 5, 4, 3, 2, 1. Okay, now here's what they want you to see. They don't really want you to multiply all these numbers together, because what they want you to kind of notice is if you start writing these numbers out, 5's cancel, 4's cancels, 3, 2, not the ones that are canceled, but the ones that cancel out. So really you're only left with 8 times 7 times 6 divided by 3 times 2. But even in that one, you can say, well, I've got 3 times 2 here. That is 6. That would cancel that 6. So really, that leaves me with 8 times 7, which would be 56. And so maybe I'd be asking, well, are they always going to kind of work their way out the way? Yeah, they will. They'll kind of balance things out so that you get some numbers that work out to be not too bad. Now, if they do something weird where they give you like the same two numbers, say it's 6 over 6. Just go ahead and kind of give this. You could lay this thing out and go through all the parts on this one, but if they give you the same number, top and bottom, that's just 1. Yeah, and sometimes it may not be that you can cancel everything out like that one, but sometimes you may get it so that
If they were like, if 3 and 2 were together like that,
Mhm.
3 and 2 were like that.
Now you can do that because it's all multiplied together. So as long as it's in a long row multiplication, you can rearrange it to make it work out that way. So, and these again, you're looking at. You got to think probability on these. You're looking for outcomes, so there's not going to be any fractions on these. You're not going to have. If I've got 10 things, I'm picking 3. You're not going to get 42.5. It's always going to be whole numbers when you go through this. And then the last problem really that we've got to look at is if you get something really big, like it's 100 and you're going to choose 2. And you may be going, okay, what do we do with 100 factorial? Because we've got 2 factorial, and then if you do 100 minus 2, that would be 98 factorial. You're like, do we have to write out all the 100 factorials? No, because here's kind of what they want you to see if you're doing one like this. Is if you do just the first few numbers, 99, 98, 97, that kind of thing, dot, dot, dot. 2 factorial is short, it's 2 times 1. When you do 98 factorial, it's 98, 97, 96. That same thing again, the 98s will cancel, the 97s will cancel, the 96s. So all those numbers below there will cancel out. You're left with 100 times 99 on the top, which is 9,900, and you're left with 2 on the bottom. So it makes 4950. So if you had 100 things to pick from and you were only picking 2, how many different ways could you come up with it? Well, there's 4,950 ways you could come up with it. Now, and again, if you're going to do the binomial theorem, if you want to watch that and see, look it up and figure out how to do that to expand a binomial, by all means, you can do that. You're going to have to do this coefficient on every single term that you go through. And it makes it a lot harder where if you do Pascal's triangle, they kind of take that guesswork out because the Pascal's triangle, the row of numbers, that's them kind of doing these coefficients along the way, and it works its way out. So